Hello, and thank you for joining us. Today's webinar topic is Improve Your Trace Element Laboratory Efficiency, Automating Sample Preparation with a SimPrep. Our presenter is Dr. Pete Winship, EMEA Sales Manager for Teledyne CETAC. If you have any questions, please feel free to submit them throughout the presentation or email Pete directly, and he will follow up with you after the webinar concludes. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Dr. Pete Winship.
Hello, everybody. Thank you for the kind introduction, and thank you, everybody, for attending today. My name is Pete Winship. I am the EMEA Sales Manager for Teledyne CETAC Technologies. I am an analytical chemist by training, so I have my experience, my background is in this area. Today we're going to be discussing trace element analysis and laboratory efficiency, and we're going to be looking at automating sample preparation. So to start with, just an agenda for this this webinar. So I just want to go through what we'll be going into. So I'll be discussing some general requirements of a trace element laboratory. I imagine this will sound quite familiar to pretty much everybody on this webinar. I want to go through a typical laboratory workflow for trace element analysis, and I always find referring back to the workflow is very helpful. Sample preparation requirements, and then the challenges of manual preparation for a trace element laboratory. Then we'll look into automating that, and then looking at a comparison between manual preparation versus automated preparation with some examples, and then we'll look at workflow efficiency at the end. So starting off with some general requirements of a trace element laboratory. So this is what will sound familiar. Trace element laboratories, they differ. There are variations between them depending on the kind of work that's going on. But trace element laboratories will be involved in, they will look at some or all of the following. So they will require robust analysis. So there will be focus on analytical accuracy and precision within a certain tolerance that's required for your analysis. There'll be focus on cleanliness of analysis, so looking for low or zero carryover, and that will feed into the accuracy and precision of the analysis. So robustness, and that is something which is consistent with all trace element laboratories. Time efficiency, this will be important to some laboratories over others, but typically there's a focus on things like sample throughput. How can we have an efficient sample throughput? There might be a requirement on fast data turnaround as well. So for some laboratories, after samples are received, there might be a data turnaround period of in some cases, 24 to 48 hours. It might be a fast turnaround for data generation. So there's a time efficiency there. And then cost efficiency as well. Trace element laboratory analysis is generally quite expensive per unit sample. So this is something to be considered as well. So the workflow of a trace element lab, this is something that I want to focus on here, and then we'll move on from there and look at sample preparation specifically. So the workflow of the laboratory. So samples are delivered, they're received at a laboratory, and overall at the end we want some data. Generate data from these samples, which again will differ between different methodologies, different sample types. So how do we get from one to the other? How do we get from A to B? Well, there's a number of steps going from sample to data, and this is where we're going to start. So sample reception. So quickly here, samples are received at laboratory. They will be, there might be just a handful of samples. You might be talking about 10 to 20 samples. You might actually be talking about a very large project. So you might be talking about thousands of samples. Those samples might come in a certain state. They might come frozen, for example, and they might just come as they are at room temperature. So regardless, those samples are accompanied by information, data on themselves. That information will then need logging, and then the analytical chemists, the lab staff, they will then put together their analytical plan to take this forward. So sample reception and your analytical plan. So the next step, based on your analytical plan, you then move into the idea of preparing these samples. So samples will need to be prepared and put into a state ready for analysis. Now, when we're talking about trace element analysis, we're not just talking about analyzing the samples, we're also talking about analyzing a number of other reagents, sample solutions with these samples, so that we get our robust quantified data. So we're not just talking about samples, we're talking about calibration standards, blanks, QCs, etc. So all of that has to be analyzed as well. The samples, they might be in a particular state where they might require digestion, they might require filtering, they might require dilution. Typically they do require dilution. They might need some spiking with internal standards or some other media. So there is a large area of sample preparation, and typically this is an area which requires a lot of focus and takes a lot longer than we typically think. When the samples are ready, we then move on to sample introduction. So here, samples are then taken on to a some sort of process which delivers them into our ICP instrument. So that will either be an ICP optical system or an ICP mass spec. Now, what we're focusing on here is liquid samples in this workflow. There are other workflows where we can look at solid samples, but we're looking at liquids in this case. So we take our prepared samples. So there are certain questions to ask next. So which nebulizer would we use? Is there a particular type that's required for this that's best suited to the sample type that's been prepared? Do we need automation? If we have a large number of samples, then most likely the answer to that question is yes. Do we have rapid introduction, a rapid introduction system involved in that process? Maybe. That's certainly something that can improve efficiency. And then are there any other considerations as well to the introduction process in terms of things like how do we do internal standardization? Are there additional gas flows involved? All of that kind of thing. So we've introduced our samples. They move on into our ICP, one at a time, obviously, where we break down our samples, our liquid samples, we atomize, we ionize, we detect those ions, or we have photon emission in the case of optical emission, and we generate our data. So that data is then output to some sort of system. That's all collected, and then we move on to processing, interpretation, and reporting on that data. So that's our whole workflow. Now, the thing to note about this is this takes time. The whole process takes time. Now, you might have a certain workflow in place with laboratory staff dedicated to certain areas here. There might be dedicated staff for sample reception, for example, or the preparation side of things. But the whole process takes time, and that time is dependent on samples that you have and the analytes that you're interested in. So today we're going to focus on sample preparation, the sample preparation aspect of the workflow. So as I mentioned, this is an area which can be quite simple or it can be quite extensive, but it's going to be dependent on the sample and the data that you want to get out of this. If you have samples that have a high level of total dissolved solid, for example, you might require digestion or filtering. That's going to take more time in the processing. But all told, what we typically hear from customers and from experience of our own, typically the sample preparation aspect of the workflow is underestimated with respect to time and effort. So this is where we're going to focus today. So, sample preparation requirements. What do we need for this? So I've already alluded to some of this already. So our samples are received. What state are they in? Are these samples that are already in a liquid state, or are they in a solid state? If they're liquid, are they? Do they have a high level of total dissolved solid, for example? Do they have debris in them? So do they need filtering? Do they need digestion? That's the first question. Then you move on to the next bit. So if you've had to digest it, you will likely then have to do a dilution step. You most likely have to do a dilution step anyway, and that's typically the case for most samples for a trace element laboratory. So what is that dilution step for? Is it to reduce the analyte concentration to bring it into a certain range so it's most suitable for detection? Is it to reduce the acid concentration if you've done a digestion on it, or another concentration of some other reagent? If so, what is the magnitude of dilution that's required? Is it something like a 10-fold dilution or a 100-fold dilution, or is it more than that? So that's the next question to ask here. What you might find in terms of sample preparation as well is that if you've got a large number of samples, say a couple of hundred samples, 200 samples say, you might have to do exactly the same dilution on all of those samples. So the same dilution factor, say a 10-fold dilution or a 100-fold dilution, might have to be applied to all of those. So then once you've diluted your samples, how do you incorporate things like an internal standard? You could spike it into your samples, or you could incorporate an additional internal standards flow through the sample introduction aspect of the workflow. That's another question to answer. Then are there other considerations as well, other additions to the sample, other spikes? A good example of this is if you're interested in the measurement of mercury, what can be done is that you can add a spike of, say, gold to your sample to stabilize the mercury that's in the sample and improve your analysis. So that's just the sample. So next we move on . Next we move on to sample preparation of, or the preparation of standards, blanks, and QCs. So these are all the samples that need to be analyzed in conjunction with the samples. So we'll start with the blank. What is an appropriate blank solution for your analysis, for your trace element analysis? That's going to depend entirely on the samples that you have and entirely on what it is you're looking to achieve. There might be some matrix matching involved, etc. So you'll need an analytical blank. It might be something as simple as, a low concentration nitric acid, for example, nitric acid solution. But it might be more complicated than that. Quality control samples. If you're doing a large project, for example, a large number of samples, you'll typically have quality controls that will contain known concentrations of the analyte that you're interested in, high or low concentrations. So what are those quality control samples and how are they to be prepared so that they are appropriate for your sample analysis? You'll always have calibration standards, so so that you get good quality quantified data from your samples. So what is the desired calibration range for that, so you can bracket the concentrations of your unknown samples. Then associated with all of that, matrix matching, is that required? Is that necessary for your blanks, QCs, and standards? So all of that is added to the preparation of your samples, which you've done. So just to reiterate, general discussion with customers that we work with and our own experience from our chemists that we have at CETAC. What we are seeing is that as we move forward, there is a greater analytical demand generally around the world. There are more samples today being analyzed than ever, and that demand has not slowed down, particularly so we've gone through the COVID period and we certainly didn't see any kind of slowdown in the requirement for sample analysis across various analytical techniques. If anything, that demand has got greater. For trace element analysis, we're also seeing a growing demand in other markets. So trace element analysis grew out from the environmental market and the geological market. Analysis required for those applications, but we're also seeing over the years, we've seen growth into the pharmaceuticals, into food testing, etc. So there is more and more trace element analysis required in wider markets than you would typically expect. Again, to reiterate, what we are hearing from everybody is that sample preparation takes time. And typically more time than you would expect. It's very easy to underestimate just how much time it takes to do the actual sample preparation side of things. There's also a focus at the moment on workflow risk. So what we are hearing from people is that where possible, it should be avoided the need to reanalyze samples after they've been run. So if, for example, you have a set of calibration standards and they're not quite right, they're not quite accurate enough, and there's too much variability on that line, that will have a knock-on effect to quantification of the analytes in your samples, and certainly the agreement with the known concentrations in your QCs. So as a result, that will have a knock-on effect to the robustness of your analysis. So going back to the original requirements for the trace element laboratory, robustness of analysis, accuracy and precision. These are all key things for analysis. So there's a focus here on trying to avoid the need to reanalyze samples. And when it comes to reanalyzing samples, it's not as simple as just reanalyzing one, because you never just reanalyze one sample. You reanalyze that one sample, but also with the calibration standards, the blanks, the QCs, etc. So it's not just as simple as doing a reanalysis. It's much more than that in terms of planning for your analysis. So risk reduction, that's another thing that we're hearing from a lot of people at the moment. So the challenges of manual preparation. So as I mentioned at the beginning, I'm an analytical chemist by training, and before I joined Teledyne CETAC, I ran a trace element laboratory for 5 years, and I was this person in the image on this slide here. So I was the person who was doing a lot of manual prep. So the first thing I would note here is that every manual preparation step in the preparation of samples, standards, QCs, blanks, etc., is an opportunity for error. So manual sample preparation, it's all about repetitive motion. It's typically transferring of solutions, liquids, etc. It's typically pipetting aliquots of sample, internal standard spike or other spikes, and then pipetting larger volumes for dilutions, etc. It all comes down to an analytical plan that you've got, but you're doing this quite mechanically. If you have a large project you're working on, I give the example of a couple of hundred samples. If you're preparing several sample racks of samples for an analysis, it really is dull work, and there really is the opportunity there for errors when the need to do reanalysis if you're focused for several hours on preparing samples in that way. So mistakes can be costly because you want to avoid reanalysis. It's incredibly time consuming, and this time can be much better spent by highly skilled people who typically have graduate degrees, postgraduate degrees that are working in laboratories. There's also health concerns here as well. If you're repeatedly undertaking the same repetitive motions, there's the risk of things like carpal tunnel. So certainly things to avoid, but it is a very monotonous process, and I can attest to that. So how can we avoid this? How can we avoid manual preparation and putting so much time into that? How can we move away from that? So what we have is we have an automated system for this to take away all of this demand in terms of manual preparation and put laboratory staff to much better use. So this is our SimPrep system. So this is something that can be put into your to automate your workflow for the sample preparation process. So what we've got here is two components here. It's 2 of 3, but we'll come to the third in a moment. So it's based on our automation, our 500 series automation. So you've got your auto sampler on the right hand side there, and then there's a syringe pump module here on the left. So we either base this system, so we take our automation, either our 2-rack automation, the ASX 280, or our 4-rack automation, the ASX 560. We combine that with the dual syringe pump module. That syringe pump module has, on one side of it, it has a smaller aliquoting syringe for taking up your sample aliquots and your internal standard spikes, etc. On the left-hand side, there's a larger dilution syringe, which delivers dilution media to overtake that aspect of the prep. And then we also combined with a piece of operating software, and those 3 components together gives us what we call the SimPrep, which is an offline liquid handling system. So what can this do? So I don't just want to focus specifically on dilution, but there are so many aspects of sample preparation that this system can contribute to. So you might want something that's as simple as a dispensing system. So what this can do is you can load up this automation with up to 4 racks in this case, because we're looking at the ASX 560 here in the image. And you can use the system just to dispense liquid. So into each sample position, you can dispense a certain volume of liquid that you want to transfer. We can do sample dilutions, and those sample dilutions can be simple individual dilutions or serial dilutions. And then that can also be applied to the preparation of calibration standards in this case. So we can do our calibration standard prep on this system and the preparation of our samples as well for dilutions. We can do spiking. So we can spike in our internal standard aliquots or any other aliquots that we need. Like I said, something like gold in the case of mercury analysis. Then we can also do things like we can split our sample if there's other requirements for that. So how does the system work? It's really quite simple. So we have our automation. Everything is operated by our piece of software. Everything is controlled. So all of the preparation processes and steps are determined by the software. So the automation is where you've got a sample probe that moves around in X, Y, Z dimensions, and it will move between a sample position, a standard position, empty tubes that we want to dispense into, and the rinse station that's on the automation. Then we have our smaller syringe, as I mentioned, and that pulls and pushes the sample aliquots that we're interested in. So it could go to a sample position and pull up an aliquot of samples, say 500 microliters for the sake of argument. And then the automation can move to an empty sample tube and dispense that aliquot with another volume of dilution media behind it so that we get our dilution. So we're taking sample from one position, moving it to the next, and adding our other components to it. So the dilution syringe, the larger syringe, that's what delivers the larger volume of media. So for example, if you wanted to do a 1 in 10 dilution, you'd send the sample probe to a sample position, pull up 1 ml of sample, and then move the sample probe to an empty tube. And then from there, you dispense the 1 ml of your sample, and that would be followed by 9 milliliters of your diluted media. Something quite simple. So just to mention this again, so not just straightforward dilutions of something like a 1 in 10. If you're interested in serial dilution, then you can operate this in the operating software, where you take an aliquot of, if you've got a very concentrated sample, for example, you could take an aliquot of that and do and make some intermediate dilutions before you get to your final. So you could do a series of, say, 1 in 10 dilutions to arrive at a 1,000-fold dilution from your original sample sample concentration. So you might do that because you've got a very concentrated sample. It could also be used in this case to do things like the preparation of your calibration standards. You can do it in serial dilution, so you've got a nice wide calibration range from that. Standard edition, so this comes to spiking. This is something where you can take your aliquot of samples. So if you look at the image on the right-hand side of the screen here, we can take an aliquot of the dark green sample. That can be followed by an aliquot of the standard for either internal standard or a standard edition spike, and then you deliver that with a volume of dilution media for your final solution, which comes to that's lighter green solution there in the right-hand tube. And then splitting, I mentioned this before. So in a lot of cases today, samples will arrive at a site for analysis, but they won't just require trace element analysis. They might require analysis of a different technique that might be in a different laboratory. So what you might need to do when samples are received is split the sample into different volumes or prepare them in different ways so that those samples can then go off to different techniques for your analysis. So for example here, again, if you look at the image here, so you start off with an aliquot of sample from the dark green solution in the sample tube. You might want to do a 10x dilution there, so that takes you to the next tube over, as well as a 5x dilution, which is the next tube over. Again, so you now got two samples from the original sample. Then you might want to do another dilution that would involve something like a spike or an additional media or something like that. So you can end up with multiple samples, in this case 3 samples here, the 3 tubes in the middle, from the original raw sample, and then they can go off for analysis. So sample splitting is another thing that you can do here. So they say a picture paints 1,000 words, but a video is even better. So what I want to do here is I want to just show you how this system operates, just to give you an idea. I'm always a big fan of looking at these and seeing how these kinds of systems and showing you how they can operate. So what we've got here, just before I start this video, is you've got your automation on the right-hand side here. So this is our ASX 560 autosampler. You've got a series of standard tubes at the back here, and then we've got 2 sample racks. And the sample rack on the left has 2 dark blue samples in, which you'll see at the front. And then on the right-hand side, the right-hand side rack, those are all empty tubes. So what we're going to do is we're going to just show a simple dilution here, sample dilution process. We've got the syringe pump module here on the left-hand side, and you can just see on the right-hand side of that module, you've got a smaller syringe. That's a 1 milliliter syringe. And on the left-hand side, you've got a larger syringe, a 10 milliliter syringe. So I'm just going to start this video. So we send our sample probe to a sample. We pull a sample aliquot, and it's held in the sample probe. And then we move the probe to a different position. You'll see that the larger syringe has filled with media as well. And then they both push their respective medias through the probe. And then you get your diluted sample in an empty tube. So something as simple as a 1 in 10. And then the sample probe returns to the rinse station, where it's rinsed outside and inside. So outside is rinsed in the flowing rinse station, and then we'll purge through liquid through the line, through the probe, so that that probe is now clean and it's ready for the next sample. So just something quite simple. But this system can work and support much more complicated processes for your sample preparation. So manual preparation versus automated preparation. So the video footage that you just saw was actually videoed quite recently. It was over the summer of this year. So what I also did this year was we put together some other video footage as well, doing a comparison between manual preparation and automated preparation. So the point I want to make here is that what you'll see for something quite simple, so just a series of standards that were prepared, and then a full rack of samples that were subject to, say, a 1 in 10 dilution. Just something quite simple. So what I wanted to point out here was just how sort of we've got on the right-hand side of the screen here, we've got the analytical chemist who's doing this by hand with a series of pipettes and just transferring liquid from different tubes. So there's a rack here, a sample rack full of samples, in inverted commas, and then there's a sample rack of empty tubes next to it. And then there's also a series of tubes here for doing standards. On the left-hand side of the screen, we've got the SimPrep that's going to do the same thing. So I'll just show you here. Let's start this process. So this is all accelerated, but just to give you an idea, we're preparing one rack of samples and some standards. So the SimPrep goes through the motions, it takes its aliquots, and it delivers the aliquots with the dilution media into the second rack, which is the one on the right-hand side of the tube. And then the analytical chemist here is doing pretty much the same. So this is all accelerated, but what you'll see is it takes around about 45 minutes for the SimPrep to complete that one rack, and then not much longer for the analyst to do the same. Now, I've tried to make this as fair as possible as well, so there's no uncapping or anything like that in this case. It's all like for like. The point I'd like to make here is that it takes a similar amount of time between the two, but if you're preparing that one rack of samples and a couple of standards, that's 45 minutes of laboratory staff time for them to actually prepare samples. Now, that's just one rack and some standards. What if it's 2 racks or 3 racks or 4 racks that need preparing for an analysis? Because if it's 2 racks based on something like this, based on our 45 minutes a rack, for example, 2 racks gives you an hour and a half, and 4 racks would give you 3 hours. 3 hours of preparation time. Now, if that was every day, that's 3 hours a day, 5 days a week, that's 15 hours of time that could be better spent doing the numerous other jobs that are required in the laboratory. So that's something to bear in mind here. So some analytical examples for you. So just to sort of bring it into the real world here and give you some examples of what the SimPrep can be applied to. So I've got 2 applications I just want to run by you. Firstly, there's quite a common one here. So an environmental application, the analysis of wastewaters and drinking water samples. So such samples received by numerous water companies on a daily basis. These samples, water samples, are analysed for various elements, various analyte elements that we want to know whether or not they're in our drinking water and at what concentration. So in this case, we've spoken to one of our customers at a water testing lab, and they've told us that they will do a 1 to 10 dilution of water samples, and they'll take them up to 10 milliliters. So 1 milliliter of sample taken up to 10 mil, and they have 200 samples a day. Now that's taking them at the moment by hand, that's taking them about 35 seconds per sample. So around about 2 hours of manual pipetting is saved here. So 2 hours for those 200 samples. So again, if you multiply that up, 2 hours in a day, 2 hours a day, 5 days a week, that's 10 hours of preparation time. That's more than a day's worth of somebody's time just doing manual pipetting. And that would be applied to numerous methodologies such as EPA 200.7 or 200.8 or many other applications in water testing. So 2 hours a day, 10 hours a week. That's a lot of time that can be saved if you can automate that process and make better use of laboratory staff time and effort. So there's a pharmaceutical application that we have been working on recently as well. So in this case, what we have is we've got some sample pellets which need essentially being dissolved into a solvent. So in, say, the first rack, so rack 1 of the automation, we have our sample pellets, and then we use the SimPrep system to dispense the solvent onto the sample. So from there, we then use some air bubbling. So we program the SimPrep to deliver 5 milliliters of air into that solvent, and we do that 3 times per sample to give it the agitation that's required to dissolve the sample pellet into the solvent. So once we've done that, we can then do a dilution on that. So we take 20 microliters of the sample from each sample position, and then 20 microliters of a standard spike. And then we deliver that with dispense it with dilution media into empty sample tubes in the second rack. So, and we take it up to 10 mil. Now, what this particular pharmaceutical customer was telling us that the SimPrep in this case could save them 4 hours a day of manual pipetting. So again, it very easily scales up. If you're looking at 4 hours a day, that's 20 hours a week of somebody's time, 2.5 days of somebody just manually pipetting. So you can see just how easy it is to make a much more efficient workflow by automating the process of sample preparation. So workflow efficiencies. So I'll just whiz through this. Obviously, there is time and effort that can be saved by going to an automated workflow for preparing samples, preparing calibration standards, blanks and QCs, etc. Laboratory staff time and effort can certainly be put to better use. So instead of, in the case of that water laboratory, 2 hours a day, 10 hours a week, you could take those 2 hours and that could be used on things like data interpretation, preparing your reports from your analysis, or even if it's just general instrument maintenance in the laboratory, or ordering of reagents, etc., email, meetings, everything that we all have to do these days in the laboratory environment. So all that time and effort can be put to better use. There's also the argument for going back to the idea of robustness, ensuring accuracy and precision. One thing that we will note is that something like an automated system, like our SimPrep system, it doesn't get tired, especially if you're talking about, like in the pharmaceutical application, 4 hours a day of manual pipetting. That's a long time to be continually pipetting liquids. So if you want to ensure accuracy and precision, if you go to an automated system, then that will certainly reduce the risk in that workflow. So all told, the key question that we always ask from this is what do you do with that time that you save? You take that time out of your workflow, you make it far more efficient, and you put it to much better use. So with that, I'd like to end that for today. And thank you everybody for your attention. If you have any questions on this, on workflows, on sample preparation, or our automated system, our SimPrep system, please feel free to email me on the email address below, or you can access us via our website, CETAC.com. But thank you for your time, and thank you.